Happy to welcome you all for today's topic on solid state. Myself, Dr. D. Anu, Assistant Professor of Chemistry, PG and Research Department of Chemistry, Sri Sharda College for Women, Salem 16. Solid state. Solid state is a study of synthesis, structure, and properties of solid phase materials. In this presentation, we are going to discuss about the crystalline and amorphous solid properties and classification of ionic compounds with a special focus on their unique atomic arrangements and bonding characteristics. We will see how these solids form through electrostatic interaction between positively and negatively charged ions, creating a rigid three-dimensional structures with distinctive physical and chemical properties. Classification of solids. Crystalline solid and amorphous solids. In crystalline solid, there is a regular arrangement of atoms, ions, or molecules, and these particles are held together by strong force. Due to the strong, they are rigid, having definite shape. Crystalline solids have characteristic sharp melting point. Crystalline solids are anisotropic in nature, which means having different physical properties in different directions. Crystalline solids are true solid. Constant particles of the crystalline solids are arranged in a long range of order. The next one is the amorphous solid. These solids have random arrangement of constant units with a short range order. The term amorphous comes from Greek word no shape. The characteristic properties of amorphous solids includes amorphous solids are irregular in shape. Amorphous solids produce pieces of irregular shapes when they are cut into two pieces. Amorphous solids are isotropic in nature, which means having same physical property in all direction. There are four types of crystalline solids. First one is the molecular solids, metallic solid, covalent solids, and ionic solids. Molecular solids. Solids are having a molecule as their constituent particles are known as molecular solid. Example, hydrogen, chlorine, water, hydrochloric acid, carbon dioxide and sucrose. Next one is a metallic solids. All metals are referred as a metallic solids. Their constant particles are positive ions. These positive ions are free moving electrons. Examples, metals like iron, aluminium, etc. Next one is a covalent solid. Crystalline solids formed by the non-metals because of formation of covalent bond between the adjacent molecule throughout the crystal. This is also known as a giant molecule. Example, diamond, graphite and silicon carbide. Next one is the ionic solid. The ionic solids are formed because of three-dimensional arrangement of cations and anions bound together with strong electrostatic force. Ionic solid made up of positive and negative ions. These ions are held together by the electrostatic interaction of oppositely charged ions. The electrostatic force of attraction between cation and anion is known as ionic bond. In case example, we are taking as a sodium chloride. Here Na plus and Cl minus are held together by the electrostatic force and this compound is said to be ionic. The formation of bond between these Na plus and Cl minus takes place by complete transfer of one or more electrons from the valence shell of one atom to the valence shell of the another atom. Properties of ionic compounds. First one is the ionic bonding. The cation and anion held together by the electrostatic force of attraction is known as ionic bond. Next one is the melting and boiling point. Due to this electrostatic force between the ionic compounds, they are having a high melting and boiling points as compared to all other types of solids. Electrical conductivity. Ionic compounds in solid state do not conduct electricity because the ions are fixed and tight. But in molten state, but in the molten state, the ions are free to move. These free ions can move and hence conduct the electricity. Next is a solubility. The ionic compounds are polar and are soluble in polar solvents. The polar solvents such as water dissolves ionic compound. The solubility is mainly due to the lowering of inner ionic electrostatic attraction and ion-solvent interaction. Ionic compounds are insoluble in non-polar solvents like carbon tetrachloride and benzene. Next is the crystallography. It is a special branch of science which deals with the properties of crystals such as their geometry and structure. The first one is the unit cell. It is the smallest building unit of crystal. The crystal consists of infinite number of unit cells. In unit cell, atoms, ions or molecules are symmetrically arranged. Next is a lattice. It is defined as an infinite set of points repeated regularly through space. The lattices are one-dimensional, two-dimensional, and three-dimensional. Next is a crystal lattice. The definite and ordered arrangement of the constituent particles, ions, or molecules extends over a large distance in crystal is called a crystal lattice. The next one is a space lattice. The position of atom, ion or molecule in a crystal relative to one another in space. Such representations are known as three-dimensional space or space lattice. Types of unit cells. There are three types of unit cells: simple cubic, body-centered cubic, face-centered cubic. The unit cell, this is one, here the 8 corners are there. So this is a one unit. When number of this unit are combined to give the crystal lattices. This unit cell is the smallest portion as a complete representation of crystal. The crystal is made up of infinite number of unit cells. There are three types: simple, body-centered and face-centered. The first one is a simple. The atoms are placed at each corners. Here all the atoms are placed only at the corners. Next is a body center. The atoms are placed at the corner as well as in the center. It is known as body center. Next is a face center. Here the atoms are placed at the corner and one in each face of the cube. So in cube we are having 6 faces. So 1, 2, 3, 4, 4 sides and front and back. So totally 6 faces are in the cube. Next is a Bravais lattice. There are only 14 possible crystal lattices which are called Bravais lattice. First one is the cubic lattice. The cubic lattice having 3 types of lattice. First one is a simple, next is a body center and next one is a face center. Here the angle between all the 3 is equal to 90 degree. Next one is a tetragonal lattice. There are 2 possible types of tetragonal lattices: primitive and body-centered. In these lattices, one side is different in length and angle between faces. So next one is the orthorhombic lattice. There are 4 types of orthorhombic lattices are possible: end-centered, body-centered, face-centered and simple or primitive centered. Next one is the monoclinic lattice. There are 2 possible types of monoclinic lattice. They are primitive and end-centered. They have unequal sides and 2 faces have angle lesser than 90 degree or more than 90 degree. Next is a hexagonal lattice. Here only one type of lattice is exhibit. It has one side is different in length to the other two and angle on the two faces. Next is a rhombohedral. Only one type of lattice is possible in the rhombohedral. It has two types such as all sides are equal and angle on each faces are less than 90 degree. Next is a triclinic lattice. Triclinic lattice has only one type of lattice. It has unequal sides and none of the angles between faces are equal to 90 degree. Next is a close packing. So close packing means how the crystals are packed in the space. So first one is a close packing. The arrangement of maximum number of ions or atoms into smallest possible space is known as close packing. In crystal atoms, ions or molecules are arranged in regular way in three-dimensional space. Each constituent atom or ion in crystals are packed in closely as possible. This arrangement has minimum energy and possesses maximum stability. So, minimum energy is required for the maximum stability. There are two types. One is a hexagonal and the other one is a cubic close packing. So first, what is mean by hexagonal close packing? In close packing, the ions are packed in a tight way. The structure consists of number of layers, one over the other. Each atom is surrounded by 6 nearest neighbors lying in the plane. The symmetry is hexagonal. The close packed layers of the ions are arranged on the alteration sequence, usually A, B, A, B. In this case, each this third layer will be directly above the first layer. This pattern of layers gives lattice with a hexagonal unit, hence it is called a hexagonal close packing. And the next one is a cubic close packing, which means the third layer are placed exactly above the gap of the first layer. In a close packed structure, the sequence of the close packed layers of the ions repeat every fourth layer of the ions is exactly same and lies directly above first layer. So A, B, C, which means in case we are like sandwich, bread, jam, butter. Again bread, jam, butter. Like this, the arrangement will be exactly same. So next one is a voids or holes. Voids mean it is a hole. That hole will look as a tetrahedral or octahedral. The unoccupied volume between layers of the close packed arrangement of spheres are called voids or holes. There are two types of holes in the crystal lattice. One is a tetrahedral, another one is a octahedral. In tetrahedral, that these holes are bound by four spheres. The four spheres lie at the regular tetrahedral and space between them is called tetrahedral holes. The coordination number of tetrahedral holes is 4. The next one is the octahedral. These are the holes bounded by 6 spheres. So total here 3 and behind the black color is 3. So totally 6 spheres. The octahedral hole is formed between cubic close packing and face hexagonal close packing. In the hexagonal close packing, 2 tetrahedral and 1 octahedral hole is present here. The coordination number of octahedral hole is 6. Polarization of ions and Fajon's rule. In ionic compounds, when a cation and anion are close to each other, the net positive charge on cation attracts electron cloud of the anion towards itself due to the electrostatic force of attraction. The size of anion is larger than cation. Due to this force, electron cloud of anion are elongated towards cation. The distortion of the electron cloud of one ion by the electron cloud of the other ion is called polarization of an ion by the cation or distortion. As distortion is increased, the bond between anion and cation takes more covalent character. When ion is easily polarizable, the valence electrons will be shared between the ions and therefore ionic character of bond will change into covalent bond characters. The net result of the ion polarization is a degree of the electron sharing or increase in the degree of covalent characters. So polarization of the ionic bond depends upon the capacity of cation to cause polarization and capacity of anion to get polarized. The polarization of ion depends upon the size of anion or cation, charge on the anion or cation, electronic configuration. The maximum stability of the ions will get in the force of attraction between the anion and cation is maximum and repulsion between anion and cation is minimum. That there only the maximum stability will be account for that compound. And next one is the Fajon's rule. The polarization of ion is increased with increase in degree of covalent character. The covalent characters are favored by small size of cation, large size of anion, high charge on cation and anion or both. Covalent bonding character increase with the decreasing cation size or increased cation charge. The high charge density of small and or highly charged cations is able to exert a powerful polarizing effect which distorts the electron cloud around the anion. Covalent character increase with the increase in anion charge or anion size. The electrons of larger, more negatively charged anions are more loosely held because they are more shielded from nuclear charge. Covalent character is greater for cations with a non-noble gas electron configuration, that is 18 electron pseudo-noble gas cations, than for cations with a true noble gas configuration, that is 8 electron cations. Next is the structure of ionic compounds. A large number of simple ionic substance crystallizes one of the following 6 common structure: face-centered cubic, body-centered cubic, cubic close packing, hexagonal and rotile structure. We will discuss about these structure, how these structures are formed. Before that, we are going to discuss about the radius ratio rule. It is a structure of ionic compound which depend upon the stoichiometry and size of the ion. The size of the ion means both cation as well as the anion. Usually cation will be in smaller size and anion will be in the larger size. So always in the close packed arrangement. So radius ratio means between the anion and cation, the radius between the anion and cation is known as radius ratio. That is, radius ratio is equal to RC plus divided by RA minus. So if you are getting the radius ratio rule, 0.4 to 0.3 means we are going to get the coordination number 6. How this coordination number means the number of positive oppositely charged ions surrounding any particular ion, maybe either cation or anion, in the unit cell of the crystal structure is known as coordination number. So if you are getting the radius ratio 0 to 0.1 means the coordination number is 2 and the arrangement is in a linear arrangement. If you are getting 0.1 to 0.2, then we are getting the coordination number as 3 and the arrangement as trigonal. In case of the coordination number 4, we are going to get a tetrahedral structure. The range between 0.2 to 0.4 as a radius ratio. And in case of the 6, that is octahedral geometry, 0.4 to 0.7, you will get the 6 coordination. It is an example for sodium chloride. So let me discuss one by one. The first one is a sodium chloride, that is a structure of sodium chloride face-centered cubic. The radius ratio of Na plus and Cl minus is 0.95 and divided by 1.81 you will get 0.5. So it comes under the 0.4 to 0.7. So the coordination number is 6. Hence the sodium chloride crystal has face-centered type structure. Hence, central metal ion is a sodium plus and it is surrounded by 6 chlorine ions octahedrally. The sodium chloride structure is also known as a rock salt structure. The Na plus, if we take this as a Na plus, it is surrounded at 8 corners of the cube and also at the center of each faces, and the arrangement of ions in the crystal lattice is called face-entered cubic lattice. Next one is the cesium chloride. The radius ratio for cesium chloride is 0.93. This value is very close to 1. The coordination number should be 8 and cubic structure. The cesium plus and chlorine minus ions have same size. These ions have simple cubic structure. Each cesium ion is surrounded by 8 chlorine at the nearest neighbors. The coordination number of both these is 8. Each cesium ion occupies center of the cube and chlorine occupies 8 corner of the cube as shown in the structure. It is a body-centered cubic lattice. Next is the zinc blend. Here the zinc blend zinc sulfate exhibit two types. One is the zinc blend and next one is the rich structure. In the structure of zinc blend, the radius ratio for Zn 2 plus and S2 minus is 0.4. The value suggests that the coordination number is 4. Each Zn 2 plus ion is contact with 4 sulfur group and the sulfur group is contact with 4 Zn 2 plus ions in zinc blend structure. In case of the rich structure, the sulfide ion present in the hexagonal close packed in two close packed layers of AB and AB, one above the other. The coordination number for the root structure is 4. The next one is the rutile structure. The radius ratio of titanium dioxide is in between 0.41 to 0.73. Each titanium 4 plus ion is surrounded by 6 oxygen 2 plus ions octahedrally and each oxygen 2 minus ion is surrounded by 3 titanium 4 plus ions triangularly. As an example for another example is cobalt fluoride, iron fluoride, etc. So far we discussed about the crystalline and amorphous solid and how the crystals, how this unit cell, what is meant by unit cell, crystal lattice, and how this ions or molecules are packed in the crystals. Then types of Bravais lattices, that 14 Bravais lattice, and how this arrangement of ions, that is hexagonal and the cubic close packing, how these arrangements are possible. Then Fedjan's rule, we are discussed about these in this lecture. Thank you.